Hi everybody. Today we're going to continue talking about solutions. I know we've been talking about intermolecular forces and the forces that are holding different molecules together and what things will dissolve in other certain substances. So today, in continuing to talk about these solutions, we're talking about different ways to describe them with their concentrations. So the first thing that we're going to talk about is whether or not solutions are dilute or concentrated. And these fall under the qualitative category. Remember, the L for qualitative means kind of quality, no numbers involved. So whether or not we have solutions that are dilute or concentrated. Now remember that a solution is made up of a solute dissolved in a solvent. So that's important to remember when we're thinking about these concentrations of solutions. A dilute solution is one that has smaller amounts of solute in a solution. A concentrated solution is one that has larger amounts of solute in the solution. So you can see that the concentrated one of this Minute Maid fruit punch is quite a bit darker than the dilute one, and that dilute one has more water in it to make it more dilute. That's it for qualitative descriptions. For quantitative, and remember this N for quantitative tells you it's quantity, we're using numbers. We're going to talk about two quantitative descriptions of concentrations. Both of them revolve around molarity. What molarity means, and we symbolize it with this capital M, molarity is the moles of the solute over the liters of solution. Okay, so that's kind of the formula that we're using to calculate molarity. And we see molarity, for example, in the lab, when we purchase the chemicals that we're going to use for different labs, different chemicals come in different molarities. So you can see this copper 2 nitrate solution comes in 0.5 molar, which is kind of a darker blue. And I know there's not much left of this one, but this one is 0.1 molar, and you can see that it is considerably more dilute than the greater concentration one. So molarity is the most common way that we're measuring concentrations, especially with lab chemicals. So for this question, what is the concentration of a saline solution containing 0.9 grams of NaCl? And saline is just a saltwater solution. 0.9 grams of NaCl for every 100 milliliters of solution. Okay, so we're looking for the moles of solute, the liters of solution. We can see we have 0.9 grams of NaCl dissolved in this solution. That's our solute. But if you look here, we're given grams and we need moles. Luckily, you guys already know how to convert from grams to moles. Grams is on top, so it goes on bottom. 1 mole goes on top, and we have the molar mass that we're dividing by. So I've already done that since you already know how. We have 0.0154 moles of NaCl. So we have our moles of solution. I can plug that into my equation down here for molarity. We have 0.0154 moles of solute over liters of solution. So the whole solution, not just the solvent, not just the dissolving solvent, but the whole solution, the solute and the solvent together. And it says that we have 100 milliliters of solution. Okay, so we have a volume, but we need it in liters. Fortunately, we know that to get from milliliters to liters, we're just moving that decimal 3 places left, and we have 0.1000 liters of solution. Okay, we plug that in to our equation down here, and when we divide, this is an easy division problem, we get 0.154 molar. And this is how we indicate the unit, molar. It's not moles over liters when we write it, but really like we saw on the chemical bottle here, 0.5 molar, and we abbreviate the molar with a big M. We can also use this molarity to calculate dilutions. So if I wanted to dilute this to make this, how do we do that? All right. How we do that is we use this dilutions formula. The dilutions formula is similar to one that we're going to see at the end of this video, and it's M1V1 equals M2V2. Okay, so that means a first molarity times a first volume is equal to a second molarity times a second volume. we're trying to make a less concentrated solution. You can never take water out of a solution really, but you can add water to a concentrated solution to make it more dilute. So that's what we're doing here. That's often what we're doing when we buy a more stock solution and we don't want this concentrated solution, we'll water it down. But we need to know how watered down to make it because we need to know what the actual molarity is for our chemistry calculations. So, what volume of a stock solution of 2 molar MgSO4 would you need to prepare 500 milliliters of 0.4 molar MgSO4? Okay, so I've done our variables list over here. We know that we're starting with a 2 molar stock solution. We want to know how much water to add to it to make 0.4 molar of to make 500 milliliters of a 0.4 molar solution. Okay, so we're just using this M1V1 equals M2V2. We have our stock solution on the left, or diluted on the right. Okay, so we know that we have 0.2 molar. We don't know what volume, so V1 equals M2 is 0.400 times 500.0 milliliters. Okay, this time we don't need our volumes in milliliters. We just need to make sure that the volumes are the same unit on each side. This is asking for milliliters, so we're going to keep that volume in milliliters. All right, so when we do this math and we divide, we get a volume is equal to 100 milliliters. What that means is that we're going to take this 2 molar solution, 100 mils of it, and we would put it into our vessel with like a 500 milliliter vessel. We'd put about 100 milliliters of MgSO4. And then we're going to fill it with water to get to the 500 milliliter line. That would give us 500 milliliters of 0.4 molar solution. Okay, so that's typically how we're diluting solutions in chemistry, for the lab especially. All right, so that's kind of an intro to solutions. We're going to use this too and kind of jump into acids and bases because we're going to see similar calculations with acids and bases. I'm actually going to go this way. So what we see is the difference between acids and bases. Hopefully you remember this from grade school if you saw it in grade school. We have acids on the left, bases on the right, and a few different ways to break them down and talk about them. You see that both acids and bases are dissolved in water. If they aren't, they're not an acid or a base. They need to be aqueous, okay? Acids are often used in the household. They're, lemons, most citruses are, or all citruses are acidic. Vinegar is acidic. Coffee, tomatoes, those are kind of acidic household items that we have. Bases are more of like bleach and baking soda. Okay, so we see those, just different uses in our houses for them. We've seen examples of acids already. Remember, we have those big 6 acids. All of them start with hydrogen. All of them end with the aqueous symbol, AQ, because they've been dissolved in water. Common ones, hydrochloric acid, sulfuric acid, nitric acid. What else? We have bases. Ammonia is a common base. Now, besides ammonia, most of our bases that we see, just like acids, start with H. Bases end in OH, with the exception of ammonia, for the ones that we're going to see in our chemistry class. So, start with H for acids, end in OH for bases. That kind of makes sense when we look at the definition that we're going to use to define acids and bases, because when they dissolve in water, acids will produce hydrogen ions. They'll break up into hydrogen ions, and bases will produce OH, or hydroxide ions, in solution. Okay, that makes sense. We can also look at acids and bases and see, help determine whether or not we have an acid or a base based on what color an indicator placed in an acid or a base turns. So if I have two substances here, one is an acid, one is a strong base, I can take an indicator, which commonly in the lab we use phenolphthalein, and that's what we'll use in our titration lab, to see what color they turn. If it stays clear, we have an acid on our hands. If it turns pink, we have a base on our hands. Okay, so we'll see that in our titration lab, but just as an example, I have the solution. I add a couple drops of the phenolphthalein, it turns pink. I know I have a base here, okay? If I take the other one, you can expect that it's going to stay clear because I already told you one is an acid and one is a base. 2 drops, and doesn't change color, okay? So that's how we can indicate, or how an indicator like phenolphthalein can be used to tell if we have an acid or a base. Lastly, the pH range for acids and bases are different. Anything under 7 is an acid, anything under or above 7 is a base. Okay? The reason for this is, for an acid, the pH is less than 7 because we have more hydroxide ions, more hydrogen ions than hydroxide. For a base, we have less hydrogen ions than hydroxide ions. Okay? And then here's a formula we're going to use to calculate pH and pOH. Negative log of H plus, negative log of OH minus. Acids, to calculate, or to look at acids and calculate the pH, we know strong acids completely dissociate in aqueous solutions to produce hydrogen ions. The concentration of the acid is what we use to calculate the pH. So the concentration that we're looking at, that's what these brackets mean, is just the molarity of the ions. And then we know that pH is always going to be between 1 and 14. It's a numeric scale, and it indicates how acidic or basic a solution is. Again, less than 7 is acidic, greater than 7 is basic. So we can use this to calculate the pH over here. We have our formula for calculating the pH. We also know that pH plus pOH equals 14. Okay? So if we knew the pH, we could find the pOH of a substance. Calculate the pH of a solution with a hydrogen ion concentration of 1 times 10 to the negative third molar. All I'm going to do is plug that into my equation. pH equals negative log of the hydrogen ion concentration, which is 1 times 10 to the negative third molar. When you put this in your calculator, and we'll try this in class, you get a pH equal to 3. Is this acidic or basic? Well, it's less than 7, and it's pH, so this is an acidic solution. Okay? Now, lastly, what we're going to look at is, this is what we're going to be doing in lab on next class. We have acid-base reaction. So we can take base and add it to acid to neutralize a reaction. It's called a neutralization reaction, and it's a double replacement reaction. You can see that because we have a strong acid, like HA, just making this up. BOH is our base. Remember, the metals, or the cation, change places in a double replacement reaction. So the H replaces the B replaces the H, and we get an ionic salt, Ba, and water, H2O. Or, in other words, H paired with OH, and that's HOH. Okay? So, a titration is a lab that we're going to be doing on Monday. This is just a lab procedure to determine the molarity of an acid or base in a neutralization reaction. We titrate to an endpoint and use that phenolphthalein solution to just get barely between clear to pink. So just a very, very light pink would be the indicator of the endpoint. And we use the same formula as before, just like M1V1 equals M2V2. We're using MAVA equals MBVB. The A for acid, the B for base. And this is what our titration will look like. We're going to have a known concentration of an acid in our Erlenmeyer flask. We use this burette to add small amounts of unknown concentration of base, and we can figure out, using this formula, what the concentration of the base is. So, an example, before we end, we have a 15 milliliter sample of a 0.25 molar HBr, titrated to the endpoint with 25 mils of KOH, potassium hydroxide. What is the concentration of the base? Well, if we're using our formula, MAVA equals MBVB, we just plug all of this in. So HBr is our acid. Our molarity is 0.250 molar. Our volume is 15 milliliter. Again, volume doesn't matter as long as we're using the same unit, either both liters or both milliliters. And MBVB, well, I don't know the concentration, so that's the unknown, MB. And the volume of the base is 25.0 milliliters. Okay. Solve for MB, which is a simple multiply here, divide by the 25 milliliters, and we get a molarity of 0.150 molar. If we want to write a balanced equation for that, we have HBr, aqueous, combined with KOH, also aqueous, it has to be dissolved in water, The cations switch places, so we get KBr, also aqueous, and water, liquid.